To start with, Lewis formulas are practically useless for group number 1 and group number 2 of periodic system. Why? Because these elements make practically no covalent compounds, and if these covalent compounds exist, they often require much better formalism of molecular orbitals. Also, Lewis structures are useless for transition metal elements. So what's left? It's p block starting from group number 3 boron and maybe with some question mark aluminum. Then most common usage is for organic chemistry for carbon nitrogen compounds, and all the way to neon. Neon makes no chemical compounds, so again it's useless. You can repeat same elements of the next period: silicon, phosphorus, sulfur and chlorine. You can also go over germanium, arsenic, selenium and bromine. And maybe with a big question mark over antimony and tellurium and iodine. And that's all. For most of other purposes, molecular orbitals will give you better model. So, when we are talking about p block elements, we must remember that we have 4 orbitals on outer shell. So we have 1 s orbital and 3 p orbital, px, py and pz. You cannot put more than 8 electrons on 4 orbitals, so you cannot make more than 4 covalent bonds. Each of them can take 2 electrons. If you have a lone pair, okay, you reduce the number of covalent bonds. So we can simplify notation just by writing 3 dots around boron, 4 dots around carbon, 5 dots around nitrogen, 6 around oxygen, and 7 around fluorine. We can do the same for the next period of periodic system. Having 3 electrons, you can make 3 covalent bonds, and that's how can you draw boron. You can make 4 covalent bonds around carbon, and that's what you always make. There's no exception. Neutral carbon atom makes 4 covalent bonds and no lone pairs. That's fantastically important information both for organic and inorganic compound. Now nitrogen with its 5 electrons can make 3 covalent bonds and has 1 lone pair. Oxygen makes 2 covalent bonds and has 2 lone pairs. Now fluorine can make only 1 covalent bond. It has 3 lone pairs, but we often omit them and never draw. If we'll take ionized atoms into consideration, we can draw additional structures. If we add 1 electron to boron, it will become like carbon having 4 electrons, so you can draw 4 covalent bonds around B minus like you draw around carbon. On the other hand, if you remove 1 electron from carbon, it will become like boron, making 3 covalent bonds only. If you remove 1 electron from nitrogen, it will become like carbon, and N plus will make 4 covalent bonds. If you remove one electron from oxygen, you can draw three bonds because it's becoming like nitrogen. It's difficult to remove two electrons from oxygen, but you can do it from sulfur, which is next in the same group, and then it will become like carbon, having four covalent bonds. On the other hand, if you will add one electron to oxygen, it will have 7 electrons like fluorine, so O minus ion will make one covalent bond. Same if you add one electron to nitrogen, it will become like oxygen, and N minus can make two covalent bonds. If you add one electron to carbon atom, it will become like nitrogen and again making three covalent bonds and having a lone pair. You can do the same thing for the next period of periodic system. So when you want to draw Lewis formulas for silicon, you simply look at carbon and replace C with Si. Same. When you want to draw something for phosphorus, you look at nitrogen and write P instead of N, S instead of O, Cl instead of F. You can go over the next period of periodic system as well. Now let's look at some examples. Example number 1. Sulfite ion SO3 2 minus. How to draw the formula as quick as we can. Remember, when we have two electrons, we always will draw one line. We may leave two electrons from lone pair. Some people draw a line for lone pairs as well. So, okay, SO3 2 minus. We'll start with oxidation numbers. Oxygen always have -2. So in this compound, oxidation number of sulfur is +4. From here, and the fact that sulfur has 6 electrons in outer shell, we can look at what happens to these 6 electrons. If I have oxidation number +4, that means that I'm removing 4 electrons and only one lone pair left. So I have something like this. S with lone pair will have oxidation number of +4. Now, let's look at what group will have one lone pair with it. So I have lone pair. It will be this one. I have lone pair around oxygen and can have 3 bonds. That's from the previous slide. Total charge on oxygen will be +1 if you'll count all electrons. Now, remember that sulfur and oxygen are in the same group, so I can use this drawing and simply replace O with S. That's what happens. So exactly the same as now. Now I can place my 3 oxygens here. I have single bonds, so all oxygens should have charge -1 to make only one single bond. And I'll have this chart. So there is lone pair on sulfur, charge +1 on sulfur atom, and three identical oxygen atoms with -1, -1, and -1. Total charge is 3 minuses, 1 plus, 2 minus. We are not making mistakes. So what's bond order here? Uh, if we'll count covalent bonds, you can see that there is only one covalent bond between each oxygen atom and sulfur atom. But bond length should be much shorter. Why? Because there is additional ionic interaction. Positive charge attracts negative charge, so you'll have something like double bond between them, one covalent and one ionic, exactly the same here and there. And you remember, we still have a lone pair left. And this is our Lewis formula. Again, each line represents two covalent electrons. It's much more helpful than traditional dot 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 representation. Next example, N2O, dinitrogen monoxide, laughing gas molecule. So how to draw Lewis formula for this? Let's look how atoms are arranged. It should be nitrogen, nitrogen, oxygen line. We do not know at this moment is it a straight line or not. Next, I'm picking up proper formulas from our chart. I need to bond both oxygen and nitrogen make 3 bonds, so I need one more bond for oxygen, so central nitrogen will be +1, which makes 4 covalent bonds, maximum number possible. Now at the right side will be oxygen that will take 1 bond because it has negative charge, so +1 -1 will make total 0, and this nitrogen will take over 3 remaining covalent bonds. So our resulting formula will be this: 3 bonds from this nitrogen, I skip lone pair, and 1 bond going to oxygen. I can draw alternative formula. In the center will be still the same N plus, but at the left side I put N minus, and now my oxygen will be neutral atom, so 1 minus 1 plus, total is neutral charge. So it will be 2 bonds coming from here and 2 bonds coming from there. My resulting formula will be like this: N minus double bonded, N plus double bonded oxygen. So my summary formula will be resonance, will be between these two, option 1 and option 2. Which is more realistic? Let's recall that oxygen is more negative, electronegative than nitrogen. So perhaps probability of oxygen being negative is higher than probability of nitrogen being negative. Nitrogen-nitrogen bond length is very close to triple bond. However, nitrogen-oxygen bond length is slightly shorter than what we would expect for single bond. It's close enough to double bond as well. So from experiment we see that both configurations work well. The necessity of using resonance shows that Lewis structures have plenty of limitations. Little surprise,